That's the first programmable computer ever created, called ENIAC. It weighed around 27 tons and occupied about 28 square meters. The thing was huge, like every computer from that era, but it could perform 300 to 3,000 math operations per second, depending on the type of operation. At that time, this was a huge leap forward, enabling the US Army to calculate artillery trajectories in real time. But that was over 80 years ago, and now computers can fit in our pockets while being around a million times more powerful than ENIAC. So, what made our computers so small, yet so powerful? Did we throw those ENIACs into a hydraulic press until the iPhone 15 popped out? Meet the star of today's video, the transistor, which revolutionized the computer industry and unlocked humanity's door to the digital era. But before we start, I would really appreciate it if you liked and commented on the video for the YouTube algorithm, and because it gives me a small dopamine hit whenever you do that. Okay, so without further ado, let's see what transistors are and how they revolutionized our world. The best way to think of a transistor is as a switch that controls the flow of current. But instead of controlling electricity with a physical switch that you push up or down with your finger, a transistor uses an electrical signal. It has 3 pins: the base, the collector, and the emitter. Depending on the type of transistor, either a positive or negative potential at the base controls the flow of current, but we'll get into that later. The collector is where the current enters the transistor, and the emitter is where the current exits, based on whether the base is active or not. So, how does it work? Why does the voltage from the base control the flow of current? It all comes down to the semiconductor material hidden inside the transistor. There are 2 types of semiconductors, type N and type P. Type N semiconductors consist of silicon atoms, each with 4 valence electrons. Silicon atoms form covalent bonds, but this makes the silicon non-conductive because the electrons don't move freely. However, if we replace some silicon atoms with phosphorus atoms, which have 5 valence electrons, we create a situation where 4 of the phosphorus electrons form covalent bonds with silicon atoms, leaving 1 electron free to move through the structure. This free electron allows the material to conduct electricity, making it an N-type semiconductor. On the other hand, P-type semiconductors use boron atoms, which have only 3 valence electrons. When boron atoms replace some silicon atoms, they create electron holes because there aren't enough electrons to complete the covalent bonds. These holes act as positive charge carriers, allowing electrons to move into them. Now, a transistor can consist of either a PNP or an NPN configuration of semiconductors. When we connect these semiconductors in this configuration, the electrons from the P-type semiconductor naturally flow to the boundaries between semiconductors to fill the electron holes. In this process, the electrons create a barrier that prevents any more electrons from the P-type semiconductor from flowing into the electron holes in the N-type semiconductor. However, when we apply a positive voltage to the base connected to the P-type semiconductor, the abundant electrons in that region start to escape from the semiconductor, thus destroying the barriers and allowing the transistor to conduct electricity. In a PNP-type transistor, instead of applying a positive voltage to the base, you need to apply a negative one for the transistor to conduct. The property of controlling the current with only an electric signal allows transistors to represent bits, which are the fundamental units of information in a computer. This ability also enables arranging transistors into different logic gates, which can perform various operations like adding binary numbers, multiplying them, and more. So that's how the transistor works. Now comes the question, why was its discovery so revolutionary? Well, computers before transistors used vacuum tubes, which controlled electricity in a somewhat different manner. Vacuum tubes work in a similar way to transistors, but instead of semiconductors, they use a cathode, a grid, and an anode. You can imagine the cathode and anode as the collector and emitter, and the grid as the base. When you apply voltage to the cathode, it starts to heat up and emit electrons. And because the inside of the vacuum tube is, well, a vacuum, the electrons can move freely and will go to the positively charged anode, creating a flow of current inside the vacuum tube. If you want to stop the current, you simply need to apply a negative voltage to the grid, so the electrons flowing from the cathode will be repelled. As you can see, vacuum tubes use a different and simpler mechanism for controlling current compared to transistors. However, the problem with vacuum tubes is that they took up a lot of space. While you could easily hold some models in your hand, building a computer out of them required a lot of space, as demonstrated by the ENIAC, which used over 18,000 of these tubes. But that's not the only problem with vacuum tubes. They often broke during the operation of ENIAC and needed frequent replacement. Transistors, on the other hand, take up far less space. Modern processors use transistors as small as 2 nanometers. To put that into perspective, the diameter of a human hair is around 75 microns, which is about 37,000 times larger than the average transistor. This allows billions of transistors to be tightly packed inside a chip roughly the size of a few centimeters, instead of taking up 28 square meters of space like ENIAC, while also being few million times more powerful. And that's the end of today's video. I hope you enjoyed it, and I would love to see you in the next one. Take care.